people here, maybe. So maybe you've gone camping or something out in the middle of the woods and you've seen this pretty spectacular sight. For most of human history before the invention of the electric light bulb, this is what the sky looked like to everyone all the time. Well, except maybe if it was cloudy. So in 1994, there was the Northridge Earthquake hit Los Angeles, and people started calling the police and the Griffith Observatory because they saw this giant silver cloud hovering over the city. And what this cloud was the Milky Way. And they had never seen this before because they'd never been outside of Los Angeles. And this is just to prove how disconnected we've become from the night sky. But imagine yourself living before the invention of the electric light bulb. Well, you would probably be pretty curious about the night sky because you were seeing this every night. Well, maybe not the magellanic clouds because maybe you're in the northern hemisphere, but still, the sky puts on a pretty great show. And comets, unlike the motion of the moon and the stars and the planets, comets are unpredictable. So if you make careful observations of the stars and planets and the moon, you might know when to plant your crops and when to have an important festival, that sort of thing. But comets, you couldn't predict these things. So comets almost universally were regarded as the product of capricious gods or bad omens or something like that. So usually in most ancient cultures all around the world, comets were seen as harbingers of doom. So let's get into a little bit of the history of comets. So many ancient people decided to record the appearance of comets. For example, the ancient Chinese were very good astronomers. They kept excellent records. And they recorded the appearance of what they called broom stars. And so the very first date back to about 1600 BCE. And in 1635 BCE, Chinese astronomers first noted down that comet tails always point away from the sun. And this is the first time that we've seen someone notice this. So keep that fact in mind, and it will be important later. And the very first record we have of Halley's Comet is from 240 BCE, and again, it's from these Chinese astronomers. And so this slide here is showing a set of illustrations from a Chinese tomb from 168 BCE, and it shows various types of comet tails and the corresponding events they are said to foreshadow, including wars, famine, and death. Okay, so moving forward and changing locations a bit, where I apologize in advance for this talk being so Eurocentric, but the relationship between Europeans and comets is very important for a modern understanding of physics and how things move in the solar system. So we'll move to Europe and the Western world, and in the West, ideas about comets were influenced by Aristotle and Aristotle's cosmology, how the universe works. So he believed that the Earth was at the center of the universe and that the moon and sun and planets and stars were carried around the Earth on perfect crystalline spheres. And since everything in the heavens was perfect and unchanging, comets had to be between the Earth and the moon, sort of like clouds, because that was the only part of the heavens that could change. And everything else was perfect. So in the medieval world, in medieval Europe, comets were seen as bad omens from an angry god. And so perhaps the most famous image of Halley's Comet we have comes from the Bay Tapestry. And this was created in about 1080. And it depicts the events leading up to the Norman conquest of England by William the Conqueror. And so the caption here reads, "These men wonder at a star." And the object of the tapestry is most likely the 1066 appearance of Halley's Comet. And although the men in the illustration wouldn't know that what exactly this comet was foretelling, it was probably something bad. And after the fact, it was reasonable to assume that this comet was signaling the defeat of the Anglo-Saxon King Harold of England by William the Conqueror in the same year in 1066. In the Anglo-Saxon Chronicles, Elmer of Malmesbury, who has probably previously saw Halley's Comet in the year 989, wrote of the 1066 comet, "You have come, have you? You have come, you source of tears to many mothers, you evil. I hate you. It is long since I saw you, but as I see you now, you are much more terrible, for I see you brandishing the downfall of my country. I hate you." That's really strong feelings about a comet. Okay. Continuing. So here, we're jumping forward a bit. This is an illustration from 1513, and it's showing disasters that happened in conjunction with two comets cited in 1456. And an old Germanic folk rhyme from about this time goes roughly something like this. 8 things there be a comet brings, when on high doth horrid range, wind, famine, plague, and death to kings, war, earthquake, floods, and direful change. Okay, so here's some more. I like these things. Okay, 2 more illustrations. The top one over here on the left is from a 1528 book by the celebrated surgeon Ambrose Paré, writing about the great comet of 1528, and he writes, "This comet is so horrible, so frightful, it produced such a great terror in the vulgar that some died of fear and others fell sick. It appeared to be of excessive length and was the color of blood. At the summit was seen the figure of a bent arm, holding in its hand a great sword, as if about to strike. At the end of the point there were 3 stars. On both sides of the rays of this comet were seen a great number of axes, knives, blood-colored swords, and among which were a great number of hideous human faces with beards and bristling hair." Okay, that's some imagination there. But still, right, you get the point. This is Bad News Bears. And below is another woodcut from roughly the same time. And this shows comets shooting out of a heavenly cannon with a man in the foreground over here being overtaken by fear. And here's another one, and this is the one I used on the poster. This is from 1668, and it's showing the destructive influence of a 4th century comet. So you comet and lightning bolts and things on fire, bad things happen. Comets are there. Here's another one. This is from 1687, showing comets as portenders of death and destruction. And one more, because I could go on all evening. This is the title page of a book. It was written in 1665. And in 1664 and 1665, there were 2 bright comets. And between them, there was an eclipse of the moon, and this was seen as an especially bad omen. And John Gadsbury, an English astrologer, wrote about these events in this 1665 book. "These blazing stars threaten the world with famine, plagues, and wars, to princes death, to kingdoms many crises, to all estates inevitable losses." He was right. In 1665, London was hit by the plague, and then the following year was the Great Fire of London. So we may be having a bit of a correlation and causation problem here. So the problem is, in medieval times, in medieval England and all on the continent as well, there were lots of terrible things that happened. And so if you waited long enough after a comet appeared in the night sky, there would be some terrible plague or some terrible fire or some monarch who was deposed from his throne. But it wasn't all bad. There was some interpretation that you could do with comets. So, for example, this is perhaps the second most famous image of Halley's Comet. This was painted between the years 1304 and 1306. It shows the adoration of the Magi with a comet as the Star of Bethlehem. So here's the Star of Bethlehem, here's baby Jesus. And so we see a comet, and this is probably inspired by Halley's Comet, which appeared in 1301, so a couple years before this painting was painted. And so here we have a comet announcing the birth of Jesus, which to Christians at that time was a good thing, right? So it's not all bad. Sometimes good things happen with the appearance of comets. Okay, so we're now at about right after the plague and the Great Fire of London. We're sort of getting into the period where the scientific revolution is starting, and we're starting to change our understanding of what comets mean. So now we move into understanding comets. So this also happens to be right around when the printing press really got going. And so here we have Peter Alpine. And so he observed Halley's comet the next time it came around in 1531. And he noticed that its tail always stretched away from the sun. And you'll notice that this is not a novel observation. Chinese astronomers writing something like 2,000 years before had also noticed this. This is maybe a lesson for all of you budding scientists in the audience. He was also not the first person to notice this with Halley's comet. He just happened to be the first person to publish this with illustrations in his book. So he gets the credit. And now we bring ourselves to Tycho Brahe. If you ask an astronomer who their favorite astronomer is, often they will say Tycho Brahe. He is one of my favorite astronomers. So he's famous because he was one of the last great naked eye astronomers. He was in favor with the Danish king for a while. He was a Danish nobleman himself. So he got the king of Denmark to build him an island castle observatory where he had really great parties, and he also did really great observations of the night sky using only his eyes and instruments. This is before the invention of the telescope. He's also famous because when he was a young university student, he got into a disagreement with his third cousin over a mathematical equation, and since neither of them could solve this mathematical equation, the only way to solve this was with a duel. And Tycho ended up losing that duel and also losing his nose. So for the rest of his life, he had what is said to be a gold nose. They recently exhumed his body and found out that it was probably a brass nose, or at least he was buried with his brass nose. Another story, which is probably apocryphal, but is one of my favorite stories, is that Tycho Brahe died because his bladder exploded after a wild night of drinking when he refused to get up to go to the bathroom. So let that be a lesson for you. Anyways, he was actually a good astronomer in addition to being a libertine. And so this is the Great Comet of 1577, as seen over Prague in November of that year. And these are Tycho Brahe's handwritten notes about this comet. So the one thing that he demonstrated, and he was rather clever about this, was he demonstrated that this comet was further away than the moon. And so remember back to our Aristotelian cosmology that everything in the heavens was perfect and unchanging, and since comets changed, they had to be inside of the moon. So how did he do this? I need everyone to do an experiment with me. So I would like you to hold out your thumb in front of your face. Okay, and now close one eye and concentrate on your thumb, and then also look at something in the background. Okay, and now open your eyes and close the other eye. And go back and forth between your two eyes. And you'll notice that your thumb moves with respect to the background, but the background doesn't change. And so that is called parallax. And what that says that if you observe something from two different vantage points, so you're observing with your two different eyes, close things tend to move compared to the background, and far things don't move compared to the background. So what Tycho Brahe did was rather clever. He observed this comet from his island castle observatory outside of Copenhagen, and he also had a friend observe the comet from Prague. And what he found out was that the position of the moon compared to the stars was different between these two observers, but the comet was more or less in the same position with respect to the background stars. And so he used this idea of parallax to prove that the comet was at least farther away than the moon, which really put a kink in this theory that the heavens were perfect and unchanging, right? So we have something going on outside of the sphere of the moon. So this brings us to Tycho Brahe's long-suffering assistant, Johannes Kepler. So if you've ever heard if you've ever taken an astronomy course, you may have heard of Kepler's laws. So this is the Kepler guy. It's also the namesake of the Kepler spacecraft that found all those planets. So what Kepler did is he took Tycho Brahe's very detailed observations of Mars, and what he figured out is that all planets orbit around the sun, and not in circular orbits, but in slightly elliptical orbits. And so these are Kepler's laws of planetary motion. And he was the first guy to come up with a model that was better than the geocentric system, where the Earth is at the center of the universe. And so this was the heliocentric system, where the sun is at the center of the universe. And this was the first time that a heliocentric model was better at predicting things than the geocentric model. And so this is why we now think, well, one of the reasons we now think that the sun is in fact, the sun is at the center of the solar system. Okay, so this was Kepler's claim to fame. Kepler is also interested in comets. So Halley's comet makes another appearance, this time in 1607, and here we have a bunch of skeletons announcing the arrival of the comet over here. So bad news bears again. Kepler thought that comets traveled in straight lines through the solar system. So planets orbited around the sun in slightly elliptical orbits, but comets went in straight lines. And then this brings us to the next comet, which is perhaps the most important comet in the history of comets, because it got the attention of two very important people. And so this comet appeared in November of 1680. And then another comet appeared in the night sky in December of 1680, and it stuck around until March of the next year. And so here's a painting of this comet over Rotterdam. It was a very spectacular comet. And in the New World, so in the colonies in the States, Increased Mather called this comet a terrible sight indeed, and the colonial government of Massachusetts proclaimed that there would be a general fast in order to seize that awful, portentous, blazing star, usually foreboding some calamity to the beholders thereof. Okay, 1680, still comets are a source of dread. Here's a German coin, again commemorating this comet. It says, "The star threatens evil, but trust in God, and he will make it well." Okay, so Edmond Halley, who was a superstar of astronomy of this time period, he was a student at Oxford. He quickly drew the attention of the Royal Society, which was the leading scientific organization in England at that time, and he was seen as someone who was both ambitious and had the intellect to support those ambitions. He made the first star map of the southern hemisphere, and in 1680 he was in Paris on his way to Rome to do royal astronomical business, or on his way to do Royal Society business, and he observed the great comet's progress across the night sky in the Paris Observatory. And then in 1682, he saw another bright comet, and by this time he was hooked. He was obsessed with comets, and he started to collect observations of comets, both the ones that he made himself and the ones that other ones made, the path of comets across the night sky. And so Halley was trying to figure out how comets move through the solar system, and also there's this problem that Kepler had described how planets move around the sun. They move in ellipses, but not why. Like, why would planets move in ellipses around the sun? Kepler didn't have an idea, and Halley wanted to figure that out, and he tried with some of his scientist friends to figure this out, and they couldn't figure it out together. And so they went to see one of the foremost mathematicians of the time, Isaac Newton. So Halley traveled in 1684 to Cambridge to consult with Isaac Newton. And Isaac Newton was a character himself. He was very mathematically brilliant, but he had been working in scholarly isolation. He tried to go to the Royal Society and present his theory on colors, and he was sort of mocked for that, not received very well, and so he decided to screw those guys, and he was just going to work by himself. So there's some feeling that Isaac Newton was probably somewhere on the autism spectrum, although it's sort of hard to, diagnose someone after they're dead, but he definitely didn't get along well with other people. So Isaac Newton had locked himself in his room, and he's working on this problem of how things move through the solar system, celestial mechanics, trying to mathematically describe the way that planets move. And so at this time, Halley shows up and says that I want to figure out what comets do. And Newton said, oh yeah, I've made these derivations before a couple years ago, but I couldn't find the papers. So how's you figured out this problem, right? Everyone's been trying to figure out this problem. Isaac Newton had already done it, sort of dismissed him. And so Halley decided that Newton should really publish this work, right? So he pushed Newton to write this up systematically and publish it. And by this time, Halley was a clerk for the Royal Society, and so he would get this done. So where did Isaac Newton's ideas about gravity come from, and ideas about how comets work? Where did they come from? So we'll start off with John Flamsteed. So he was the first royal astronomer. He was appointed by Charles II in 1675 to run the new Royal Observatory in Greenwich. And so Flamsteed proposed that those two comets, those two 1680 comets, were actually the same comet that had one going towards the sun, and then it turned sharply away and came back. And he thought this was due to magnetism. And so Newton thought that this was, not right at all. Number one, if you had an iron comet and it got close to the sun, it would heat up and then it would lose its magnetism, and that wouldn't work at all. And so Newton didn't believe him until Newton started corresponding with Robert Hooke. So there are actually no paintings of Robert Hooke that survive to this day. And so this is a painting based on the recollections of what he looked like from his colleagues. So just imagine that your colleagues, have to describe what you looked like to make a portrait of you for posterity. So Robert Hooke, if you've ever taken a physics class, you may have heard of Hooke's law. This is a law of elasticity that says what happens when you pull on a spring, what happens to the force as you pull on a spring, and this is a very simple mathematical equation that describes this. So Hooke had the idea that planets orbiting the sun should work the same way. So his idea was something like the sun pulls on the planets and it gets stronger the closer you are to the sun. And although he claimed to have wrote this down mathematically, he never produced this work. And so he must have just had this intuition that this is how it worked. And then after Isaac Newton corresponded with Hooke for a while, he was like, yeah, you know what, I think that's right. And it was Isaac Newton that actually came up with a mathematical formula for how planets orbit around the sun. And he had a correct working formula by about 1684. This happened to be the same year that Hooke showed up in Isaac Newton's office and said, I want to figure out how comets work. And so this led to the publication of the Principia, which is perhaps the most important publication in all of physics, or maybe the most important scientific book ever written. So it presents to the world Newton's theory of gravity and its laws of motion. And just about the time that Newton finished writing this book, Halley's like, okay, we got to publish this. This is really super duper important. But the Royal Society had just blown its entire budget publishing something else. It was the History of Fishes. It was a very nice illustrated book about fish. Maybe not as important as this, it was very nice. So Halley decided, he was the only one at the Royal Society who understood how important this book was, And so he paid for the publication of the first edition of the Principia himself. And this came out in 1687. Okay, so now I have a question for you all, just to make sure, to see if you're paying attention. Okay, so we say that the moon orbits around the Earth because of gravity. We also say that an apple falls to the ground because of gravity, right? But those seem to me like two very different things. So are these two things that we call gravity the same thing, or are we using the same word to describe two different things? Okay, so I want you to think about that for a second. Okay, so show of hands. Don't be shy. So who thinks that these two things we call gravity are in fact the same thing? And who thinks that they are in fact different things? So, yeah. Okay, so for most of human history, we thought that B was in fact correct. We weren't calling them gravity, but we thought that there was no connection at all between things that go on in the heavens and things that happen here on Earth. But they are in fact the same thing. And Isaac Newton was the first person in the history of the world to figure this out. So in order to understand how this works, we'll use something called Newton's canon. So this actually didn't appear in the Principia, but it appears in books written shortly after. So let's imagine that we have a cannon on top of a very tall mountain. And so we shoot the cannonball, and it falls down to the earth. Okay, so let's put some more gunpowder in our cannon, and it shoots just a little bit further. Okay, so let's put like a lot of gunpowder in this cannon, and we're going to shoot this cannonball like really, really far. So the farthest you can shoot the cannonball is just so it just goes all the way around this big arc and just barely hits on the other side of the world. Okay, so what if we put even more gunpowder in our cannon? What would happen? Well, you go around, but you wouldn't hit the earth. So you just keep going around in a circle forever. And that's called an orbit. Right? So the orbiting is the same thing as falling, this is a really profound thing. So that means that the force of gravity that causes things to fall to the earth is the same thing that causes things to orbit around other things. So this is the only fold-out and the only actual picture in all of Newton's Principia, and this has to do with the orbit of comets. Maybe because Halley was paying for the book. So here we have a comet going around the sun. So at first, Newton agreed that comets had to travel through straight lines in the solar system, just like Kepler thought. But then he came around to it that no, comets travel in sort of these U-shaped orbits, or maybe these are really, really, really long ellipses through the solar system. And so this verified Kepler's ideas about how things orbit around other things. Things orbit around the sun in ellipses. And so now we have the mathematical ways to describe how objects orbit around in the solar system, including comets. So Halley took Newton's mathematics and he published his own works. Remember how Halley was collecting all of these observations of comets? Well, now he could compute the orbital parameters of these comets' orbits. And so he computed the orbits of 24 comets in his 1705 work, Synopsis of Cometary Astronomy. And so it says, this table needs little explanation since it's plain enough from the titles what the numbers mean. Very good. So he noted that the vital statistics of 3 comets, those that appeared in 1531, 1607, and 1682, bore a remarkable resemblance. So all of these comets had the same orbital parameters, and so these were probably not 3 separate comets, but in fact the same comet returning at regular intervals. And so he boldly predicted that this comet would return in 1758. And this prediction came true, although he didn't live to see that since he died he predicted it would come back in 1758 and he died in 1742, so before the comet came back. But right around the time that the comet was supposed to come back, there's this great push to calculate exactly when it would come back. And so this actually ends up being sort of a hard mathematical problem, since you can't actually write this down in a nice formula, because not only is the sun pulling on this comet, but also the Earth pulls on the comet, and Jupiter pulls on the comet, and Saturn pulls on the comet, and Uranus pulls on the comet, and Neptune pulls on the comet. And so you have to keep in mind all of these different pulls in order to actually calculate the orbit of this comet. And so how you do this is you have to have the comet here, and then you calculate all the forces on it, and then you step it forward a bit, and you see where the comet goes, and then you calculate all the forces on it, and you step it forward again. And so this is a very hard mathematical problem to do by hand. So just imagine doing this all longhand with big tables of numbers. So now we do this with computers, and there's some very clever people who can calculate the dynamics of everything in the solar system for billions of years up to machine precisions in computers. But several groups of people went and they calculated the orbit of Halley's Comet to predict when it would come back. And so there was a prediction that it would come back in March of 1759, once you do all of the complicated math. But Uranus and Neptune actually hadn't been discovered yet, so they didn't include that in their calculations. So it actually came back a month earlier than expected. But it did come back in 1759, proving once and for all that Newton's mathematics worked. And this was really the first really big test of Newton's celestial mechanics. And so this comet was named after Halley in his honor, and it comes back every 76 years or so. So here we have confirmed observations of Halley's Comet every 76 years. So the last one was in 1986. So I have a sister named Haley who was born in 1986. My mother claims that this is a coincidence. I don't know if I believe her. And the next time Halley's Comet will come back is in 2061. So let's explore a bit in detail Halley's Comet coming back in 1910. So one thing that led to comet mania in 1910 was actually a different comet that appeared. It was actually more spectacular than Halley's Comet, and this was the Great Daylight Comet of 1910. Here's a photograph of it. But here is a photograph of Halley's Comet from 1910. This is the first time that we ever photographed this comet. And this is also a demonstration of how a little bit of scientific information in the wrong hands can be disastrous. So at this time, we had the first spectrographs. And what we did is we took light reflected off of the comet and we spread it out, and we could see what molecules there were in the tail of the comet. And what we found was that there was cyanogen gas in the tail of the comet. And so people rightly feared that maybe they would get poisoned by Halley's Comet. And it didn't help, or it didn't hurt, that as the comet started approaching, astronomers announced that we would actually be moving through the tail of Halley's Comet. And so astronomers assured everyone that it's perfectly safe, and the gas is so diluted that it won't hurt anyone. But that didn't stop people from publishing stories in newspapers about the danger of comets, or Halley's Comet, this poison gas from the comet. People sold comet pills, which were said to counteract the effects of the poisonous gas, and these actually sold rather well. And so on May 20th, 1910, Earth passed through the tail of Halley's Comet, and everyone who had taken the pills were still alive. But of course, everyone who had not taken the pills were also still alive. So here we have a French postcard dated from 1910, sort of a satirical postcard making fun of people who are panicked over the appearance of Halley's Comet. This was the age of the postcard. But there were also some cool cultural artifacts of this comet. So both for the 1835 and the 1910 passing of Halley's Comet saw an uptick in comet jewelry. So here we have a enamel and opal and gold brooch depicting Halley's Comet. So I already have my outfit picked out for the 2061 appearance of Halley's Comet. I plan on wearing this 1932 Chanel diamond-studded comet necklace. I think it's rather fetching. But also we have cultural artifacts like this. This is ragtime, so this is the Halley's Comet rag. Okay, enough of that. So you can see there's great excitement about Halley's Comet, but there's also widespread panic, and this continues to this day. So this is, again, this is Comet Hale-Bopp. This appeared in 1996, and so this is a photo of Hale-Bopp over Indian Cove in the Joshua Tree National Forest in California. And so in 1996, amateur astronomer Chuck Shamarek of Houston, Texas, photographed this comet, and in his photograph of the comet, he showed a fuzzy, slightly elongated object nearby the comet. And what did he do? He called the Art Bell radio program Coast to Coast AM. And so if you're not familiar with this radio show, Art Bell is a proponent of UFO conspiracy theories. He thinks that a lot of world leaders are secretly replaced with reptilians. And so he says that there's so this amateur astronomer calls in and says that there's a Saturn-like object following Hale-Bopp. And so a lot of UFO enthusiasts decided that this object was in fact a UFO traveling along the comet Hale-Bopp. And so several astronomers ended up calling into this radio show, including Alan Hale of Hale-Bopp fame. And he said that no, this object in the photograph is in fact a star. And the amateur astronomer who found it just hadn't set up his star catalog program correctly. But whatever, this didn't dissuade anyone, or maybe dissuaded some people. So then Art Bell claimed that he got this secret photograph that these astronomers are about to publish that showed a UFO right alongside Hale-Bopp. But then later, two University of Hawaii astronomers said that that was actually their photo that they had taken, and the photo was doctored to show a UFO. Okay, so in March 1997, an American UFO religious group, were sort of millennialists, decided that the world was about to end, and they were called Heaven's Gate, and they committed mass suicide because they decided that they wanted to go see, or wanted to go up to this UFO with the comet Hale-Bopp. So again, we have these really great impulses, like these really gorgeous comets, but there's also some sort of death and destruction that goes along with the comet. So one more thing before I tell you a bit in the remaining time I have about what a comet is. I would like to tell you a story about a teenage amateur astronomer, Elijah Wood, who in May 1998 discovered an unusual object in the night sky during a star party for his high school's astronomy club. And his teacher sees this unusual object, and he notifies an astronomer who realizes that this comet is on a collision course with Earth. And this is, of course, the plot of the 1998 movie Deep Impact. So remember this name, it's important. Let's move on to our modern understanding of comets. What are comets? So a comet is an amalgam of rock and dust and water ice and frozen gases like carbon dioxide and carbon monoxide and methane and ammonia. And they've been described as dirty snowballs or icy dirt balls, depending on how much dust there is. in your comet. And so the nucleus of your comet, that's sort of the inner rocky bit, is usually thought to be covered in dust, and underneath that is water ice mostly. And so comets tend to have two tails. Sometimes the two tails are visible, more visible than others. So how this works is that you have an ion tail here, which is ionized gas, and you have a dust tail here too. So the ionized tail is carried off by the solar wind, and you also have photons, that's particles of light from the sun, that run into dust particles and also knock them back. But the ions are pushed a lot harder than the dust is, so sometimes these tails separate, and often the dust tail will point away from the sun but sort of curve in the direction that the comet came from. So where do these comets come from? Well, they come from the Oort Cloud, which is sort of a theoretical place in the solar system. We've never observed it because it has all of these icy bodies, which there's not a lot of light out there, and these aren't very shiny, so they're very hard to see. But they're thought to be this reservoir of comets that live out in the outer solar system. So this is something like a light year across here. And every now and then, objects in the Oort cloud will collide with each other, or a star will pass by, and this is enough to knock these comets into the inner solar system. And so there's several types of comets that we see. There are short period of comets that are inside the orbit of Jupiter. There are slightly longer period comets like Halley here, and there are very, very long period comets like Hyakutake, which has a 17,000 year period. So it takes 17,000 years to come back after we see it once. Another piece of evidence we have why we think these things are knocked into the inner solar system, you can see that all the planets orbit in this nice plane, but Comet Halley here we see is very inclined compared to the rest of the disk. Okay, so how do you observe comets? Well, there's one easy way to do it. So this is the SOHO telescope, and it's pointed at the sun. And you see here there's actually a disk in front of the sun. It's meant to observe all this stuff coming off the sun, and that's cool in itself, except that it makes a really great comet hunter. So SOHO has actually discovered over 3,000 comets since it was launched in May 1996, and this is actually about half of all known comets have been found by this one satellite. And actually they've been found by amateur astronomers who comb through the SOHO archives. And there's one guy who's found over 140 comets, Mike Oates. So here we see Comet Ison breaking up as it goes around the sun. Okay, so that's the easy way to find comets. Just point something at the sun and wait for comets to go around it. So what's a more difficult way to observe comets? Flybys. So this is black diamond difficulty. Here we have the very first flyby of a comet. It's a flyby of Halley's Comet by the European Space Agency probe Giotto, who is the same guy who painted that Adoration of the Magi with a little comet over it, so that's named after him. So here we have a flyby of Halley's Comet. And this is the first time that we ever saw what the nucleus of a comet looked like. So it's kind of blurry, but still, pretty impressive. So we found that the ejecta material here is something like 80% water, 10% carbon monoxide, and the rest is a mix of methane and ammonia with some hydrocarbons, iron, and sodium thrown in there for good measure. Okay. So the next time that we flew by a comet was in January 2005 when the Deep Impact spacecraft, you remember that from the movie, actually slammed something into a comet to see what it was made out of. So there we go, boom! So we slammed a probe into the comet and observed it. It actually ended up being a lot more dusty than we expected, so we didn't actually get a good view of it. Here's a view from the impactor. Okay. So the next one, this is actually a deep impact. They continue. They steered it to another comet. So this is Epoxy, which is deep impact but renamed, flying by the comet Hartley 2 in 2010. Let me see it again. So here's another one. This is NASA's Stardust spacecraft flying by another comet in 2011. And this one is cool because not only did it fly by the comet, but it also sent something back. So the sample return capsule successfully landed on the Earth in Utah. It actually entered the Earth's atmosphere at a velocity of 12.9 kilometers per second, which is the fastest man-made object ever to re-enter the atmosphere successfully. And they got particles of comet dust out of this. And so they found a wide range of organic compounds, including biologically usable nitrogen and amino acids, as well as silicates. And this sort of proves our understanding of the solar system. How it formed is more or less correct. So it has the same sort of silicates that we find in asteroids, but it also has this really complex organic chemistry. And so here's another view of a little comet particle. And so we have flown by several comets, so that is the one black diamond difficulty. Orbiting a comet would be double black diamond difficulty, and we did that too, very recently. This is the Rosetta Spacecraft, or an artist's illustration of the artist's impression of the Rosetta Spacecraft. And it was actually supposed to orbit a different comet, but at the last minute, it was delayed because there was a problem with the rocket that used to launch it. So they decided at the last minute to switch comet targets. Not gonna work. Okay. And so now it is orbiting around the comet 67P Cherenkov-Gerasimenko, which is hard. So we'll just call it 67P for now. And so here's a selfie taken of the spacecraft. You can see a solar panel here, and there is our friend 67P. So it actually took a rather circuitous path to get to our comet. This is why it's double black diamond difficulty, and we have in fact been successfully orbiting around this comet since 2014. And on its way, we observed 2 asteroids. And now here we go, the main show, Comet 67P. This is a really unprecedented view of what the nucleus of a comet looks like. And so this is a short period comet. It has an orbital period of 6.5 years, and we've been seeing it orbit around the sun since 1969. And so you see this two-lobe structure here. It's probably because we had 2 objects impact each other very, very, very slowly and then stick together. So here is a computer model of what this looks like, the comet. And so I have been told that this sort of looks like a rubber ducky. So if you don't already, I would suggest following the Comet 67P on Twitter. It's rather amusing. So here you go. So this bit here is something like 2.5 kilometers wide, and this bit here is something like 4 kilometers wide. And so we can actually measure the volume, and we can measure how much it weighs by how it perturbs the orbit of the spacecraft around it. And it's actually less dense than water, so this thing would float in a bathtub. So for scale, there you go. So this is a European spacecraft, so we only have European cities. But this is the comet compared to Paris in London. So what did we learn about this comet? Well, one thing that we learned is there was a theory that most of the Earth's water came from impacts of comets on the Earth. But if you actually look at the isotope ratios of water on this comet, they're actually different on the comet than the water we find on Earth. So the water from Earth probably didn't come from comets, and it may have come from asteroid impacts instead. Asteroids are in the inner solar system. They get irradiated by the sun. The water is a little different than these things that come from the very, very outer solar system, where there's very, very little sunlight. And we also found a lot of free oxygen, the gas coming off of this comet. And we would have thought that all of this oxygen would have been incorporated into water on the comet, but there seems to be some primordial oxygen incorporated inside the center of the comet. And we've also been watching these really cool geysers come out of the comet, of these gas spewing out. We see these craters forming and all sorts of neat geology happening on the surface of the comet. So where is it now? So the comet has already gone past the closest point to the sun, and now it is traveling back out to the outer solar system. Okay, so we already did 1 black diamond difficulty and 2 black diamond difficulty. So now this is like, I think this is 12 black diamond difficulties landing on a comet. So the Rosetta spacecraft brought along a friend with it, the Philae lander. So Rosetta is named after the Rosetta Stone. And Philae is actually another tablet that translated ancient Egyptian and Greek at the same time. So that's where the name comes from. So we want to land this little thing on a comet. This is really, really hard to do. Mostly because the comet is not very massive, and so it's really easy if you land something on the comet for it just to bounce back, because the comet doesn't have very much gravity to pull whatever thing you have onto the comet. So the escape velocity is something like 1 meter per second. So if you jump up with a velocity of 1 meter per second, you fly off the comet and you're gone forever. So here we have the Philae lander falling. This is taken from the Rosetta spacecraft. Actually, here we go. You can watch it fall down onto the comet. Okay, maybe in the interest of time, we'll keep going. So this is taken from the Philae lander. This is going onto the comet. You can watch it fall this way. And we're going to descend down onto the surface of the comet. So this boulder right here is about 5 meters in size. Boom. Okay. So this is where our lander touched down. The problem is, in order to successfully land on the comet, you need to have harpoons that anchor into the comet, and those did not fire correctly. So what ended up happening is the lander bounced on the surface of the comet. Boom. So it went something like that. So, not great, but not terrible, because it didn't fly off the comet, right? So it ended up landing here. So this is a view from the comet from the Philae lander. So we actually did successfully land on the surface of the comet. That's awesome. We actually managed to accomplish about 80% of the Philae lander's science goals before it ran out of power and had to turn off. So what did we learn from the Philae lander before its batteries ran out? We learned a lot about the dust layer on the outside of the comet, how much dust is there before you hit ice. And we also learned about the magnetic field of the comet. So there was an idea that a comet would have an intrinsic magnetic field, and that had something to do with the formation of comets out in the Oort Cloud. But what we found was that there was no magnetic field in the comet. So I think I'm going to close with this video.
A year had passed since Rosetta had arrived at her new home, Comet 67P Churyumov-Gerasimenko.
There we go.
It had been a busy time for Rosetta and for her lander Philae. who had been sent to the surface of the comet. Rosetta didn't go exactly as planned, but Philae still managed to make his first measurements of the comet's surface before his battery ran out and he fell into a long, deep sleep. Rosetta continued studying the comet, learning new and wonderful things as she followed it on its journey through the solar system. It measured 4 kilometers across, and from the gravitational pull that Rosetta felt, she could calculate the mass of the comet, 10 billion tons. Although the comet looked like a giant rock, it was made of something much lighter, so much so that it would float on water. As the comet got closer to the hot sun, Rosetta saw its activity increase. She collected samples of the gas and dust that streamed into space in order to learn more about what the comet was made of and where in the solar system it was born. One of the most important questions scientists back home wanted to answer was where Earth's water came from. Could it have come from comets and asteroids billions of years ago? Rosetta was surprised to discover that the water vapor flowing away from her comet came from older Earth's oceans. Scientists wondered what it would mean for their theories of how the solar system evolved. There were many other types of gases too, and it smelled like a weird mixture of rotten eggs, horse stables, and marzipan. Rosetta also collected thousands and thousands of dust grains, small and large. Some of them seemed very fluffy, like the head of a dandelion. As the days and weeks passed, the comet looked more and more spectacular. Rosetta flew close by to get a better look, but there she found herself surrounded by a lot of dust. Although it wasn't as dangerous as when Grandfather Giotto flew past Comet Halley at high speed 100 years ago, Rosetta still became disoriented and almost lost her way, so decided to continue her work from a safer distance. Rosetta began to see the surface of the comet changing as it got nearer to the sun. She saw jets of dust coming out of pits and patches of ice being revealed. Even though the comet was becoming more active, it was still quite cold on the surface. Rosetta measured temperatures around minus 100 degrees Celsius, and it was even colder underneath. Thinking about the cold, she worried about Philae, who had been asleep for several months. She didn't even know exactly where he had finally landed, and wondered whether there was enough sunlight there to recharge his batteries. Then, one Saturday in June, she received a phone call. It was Philae. She quickly told everyone on Earth. Rosetta wanted to tell Philae all that had happened while he had been asleep, and the many exciting things she had learned about the comet, but the connection wasn't very good. It was very frustrating, and Rosetta had to move to different locations to try to find the best spot for a better connection. Philae hoped he would soon be able to do more experiments on the comet's surface, while Rosetta studied it from afar. As the comet reached its closest point to the sun, Rosetta and Philae were very excited to witness this once-in-a-lifetime event. And they looked forward to seeing what would happen to the comet over the next year as they headed back towards the outer solar system.
Unfortunately, we never established contact with the Philae lander again. We think the antenna is broken. So poor little Philae. But we have learned a lot about comets from Rosetta and Philae. And they have a whole series of really adorable cartoons on YouTube if you want to watch them. So just to conclude here, tonight we learned a little bit about the pre-scientific view of comets harbingers of doom. We learned about how comets were very instrumental for figuring out the physics of how things orbit around the sun. And we also learned a little bit about what it's like to explore things in the solar system from moderately difficult to super duper 12 black diamond difficulty. So, thank you very much for your kind attention, and I'll take some questions.
So because they send out a lot of material into space, do comets eventually kind of disappear or like get destroyed?
Okay, so do comets eventually disappear? The answer is yes. So we saw the one comet going around the sun and just sort of petering out. So it depends on the comet how long they last. So some of them come into the inner solar system, get flung around the sun, survive this one trip, go out into the outer solar system, and are never heard from again. If you keep going around the sun, eventually you're going to become so unstable you sort of disintegrate into a pile of dust and very small pebbles and rocks. And every now and then we actually run into this pile of very small pebbles and dust and rocks, and that's what causes meteor showers. So a couple times a year we run into these things, and it makes a spectacular light show on Earth. Okay, in the very back.
That actually raises a question I'm always curious about. Since the conglomeration of dust and pebbles that is in the comet orbits in one particular orbit with one particular return time, how is it that we run through these trails of comet trash at the same time every single year? How come the material gets so spread out in this orbit? I can't understand that.
Okay, so the question is, why do we run into this stuff once a year? It gets a little bit spread out as it goes through its orbit. So I think it has. I'm not entirely sure on the exact orbital mechanics of this. But so these things do orbit around the sun, and the Earth orbits around the sun, and our orbits just happen to cross each other at that particular point in the year. So I'm not sure of the exact geometry of everything. And also, so we're orbiting in a plane, but comets also tend to orbit in a different plane than the rest of us, so that might have something to do with it as well. Sorry I couldn't be more helpful.
So you said that when a comet goes around the sun, it loses some of its mass in terms of dust particles.
Yeah.
So then, when the mass changes, the gravitational pull also changes. So how come you're able to predict the orbit every time?
Right. So the mass of the comet changes a bit when you go around the sun because you're losing dust and gas and stuff. And so, how could you predict the orbit of this if your mass is changing? So I think the answer to this is your mass is not changing very much. So you're not actually losing that much dust and gas off of your comet every time you go around the sun. So it changes your results a little bit, but not enough to be significant. So if you really wanted a very sophisticated model of where exactly your comet was, you'd have to account for this mass loss. But if you're someone working in the 1780s trying to figure out where your comet will be, this is just a very small perturbation on the bigger gravitational pull of stuff. Yeah, right there. Yeah.
Am I to assume that some of them they disintegrate, some of them recharge themselves once they go into this part of the space that we don't know anything about? You said that this particular one collided with some other one and became a bigger mass. So does this perpetuate some of these comets like we have now?
Yeah, so some comets disintegrate, but do some comets sort of bulk up when they go back out to the Oort Cloud? The answer is probably not. Right, so the Oort Cloud is very, very far away, and it takes hundreds of thousands of years to come back into the inner solar system. And usually if you collide with something out there, it messes up your orbit, so maybe you don't get kicked into the inner solar system anymore, you get kicked out of the solar system entirely, and you float through space forever. That sort of thing. So usually the only thing that comets do is lose mass. Sometimes things in the outer solar system will very slowly coalesce with each other. I think it happened more in the early solar system when there was more gas around to sort of moderate things and make things slow down, and then the gas sort of dissipated out, and now we're just stuck with all this rocky stuff that we have. Over here?
Do we have any idea of the density distribution of the Oort Cloud system?
So do we have any idea of the density distribution of the Oort Cloud? So the only way we know anything about the Oort Cloud is from comets, right? And we sort of know how dense most comets are. The only really superb measurements we have is this one object, this 167P comet that we measured, because we've had something orbiting around it and measured its gravity really well, so we know its mass really well, and so we know its density really well. We have some idea of the density of some other comets that go into the inner solar system, so we sort of have some idea of what most Oort Cloud objects are made of. But again, we have a very small sample. So we know a lot more about asteroids and planets and that sort of thing than we do about comets. Yeah.
Is it science fiction or science? We hear talk that supposedly work is being done on dealing with eventualities should heavenly bodies come too close to the Earth. Now, is that science fiction, or are scientists actually working on those problems?
Okay, so the question is it science or is it science fiction that people are working on solutions for comets or asteroids hitting the Earth, like that movie Deep Impact, or the movie Armageddon, which came out the same year? That was an asteroid, not a comet. So the answer is sort of. There are actual scientists who are working on this problem. They've published solutions for how you could deflect something. So the best ideas that I've heard is to just keep nudging it a bit until it moves enough that it won't hit the Earth anymore. So you do that with a series of bombs or something. What you don't do is the Armageddon style blowing everything up, because then you just create all the shrapnel which falls into the Earth. The problem is there's not really people interested in funding this as much, so we don't have the system ready to go. So if today we realized that there was going to be a comet that was going to hit us in a month, we'd be screwed. There is money for cataloging all of the near-Earth objects so that we have a better warning if something's going to hit the Earth. And the US government actually gives astronomers a lot of money to do this. So, for example, the Pan-STARRS telescope is a telescope that's trying to photograph a bunch of stars every night to see if their brightness changes, but they also got money to do a survey of asteroids that might just happen to fly in front of the telescope, and they use that money to fund their other astronomy business. So there are people working on this problem. There's not anything built right now, and we are trying to catalog all of the things in the inner solar system.
How come Chelyabinsk snuck up on us with no detection? Nobody's.
So why did the Chelyabinsk object, so it was a meteor, hit the Earth and we didn't know anything about it? Partially it was from the angle it was coming from. So it was coming from an angle where the sun was blocking out a lot of our vision. It was also sort of a very small object. So the smaller your object is, the harder it is to observe it. And so it was a combination of just bad luck with the angle and it being very small. There's actually another near-Earth object that was passing by the Earth the same day. It was coming from a different angle, and we did see that one. But, the sun gets in the way. It's hard to observe things through the sun. Lousy star. What else in the back there? Yeah?
Yeah, I was wondering, what about mining comets? Is that science fiction, or are there valuable things in there.
So mining comets. I've not heard any proposals to mine comets. I've heard proposals to mine asteroids. So there are plans to build something where you would capture an asteroid, or you capture a piece of the asteroid and bring it back so that it would orbit the Earth, and then you'd send up an astronaut to go mine chunks off of your asteroid to get rare earth elements or something like that. Comets are sort of mostly ice and dust and organic compounds, which are probably not as valuable as sort of the mineral-rich asteroids. Yeah.
What was the result of the impact of the comet with Jupiter?
What was the result of the comet of the impact of Jupiter? So it made those brown patches on Jupiter, so it exposed some layers sort of in the some layers of the atmosphere of Jupiter that we hadn't seen before. And so those spots stuck around for a couple months, I think, and then that was it. So to Jupiter as a whole, not much. It gets hit by stuff all of the time, fairly frequently. But it was an opportunity for us, because we can't slam things into Jupiter, to learn a little bit more about the atmosphere layers of Jupiter.
I wanted to know, like, when the comet gets to its closest point towards the sun, the sun's gravitational force is able to like give the comet kind of a push back towards the Oort Cloud. But what's the force that makes the comet able to turn back around back towards the sun, like in the Oort Cloud?
Okay, so so you have a comet and it's coming in and it turns around the sun and then it goes back and then it goes on this elliptical orbit, right? So it comes back around. Well, the answer is gravity the whole time, right? So it's the same reason that the Earth keeps going around the sun all the time. So the sun is constantly pulling on the Earth, saying, come here, come here, come here. But the Earth keeps wanting to go forward. The Earth wants to travel in a straight line, and your comet keeps wanting to travel in a straight line, and it keeps getting pulled a little bit by the sun. And the way that it works is it's pulled a lot more when it's close to the sun, and it's pulled a lot less when it's farther away. So it'll speed up as it gets near the sun, and it gets flung out. And when it's at its furthest point, it gets pulled back in again by the gravity of the sun. So it's two things. It's gravity, and it's the conservation of angular momentum, which is a little hard to explain, but that's just saying that once you get something going in a circle, it wants to keep staying in a circle. And you actually have to perturb it somewhat. You have to knock the comet somehow, or it'll just keep going in this elliptical orbit forever. Here.
Like you have that slide that there was a comet that was coming back every 17,000 years.
Yeah.
How can we know?
So how can we know the comet's coming back every 17,000 years? Because we don't have 17,000 years worth of observations.
Yeah.
So we can make our best guess. So we can trace out the orbit of the part that we can see, and then we can, based on that, we can calculate the other part of the orbit that we can't see. So we believe that Newton's laws of planetary motion are true, even in the distant past and in the distant future.
And how come this one is not knocked out by something else? Wow.
Yeah, so why is it knocked out by something else? Well,
why is it not?
Yeah, so the problem with the Oort cloud is actually that things are very, very far apart from each other. So it's very unlikely that if you have a comet just hanging out there going in a very, very long orbit through there, that it will ever hit anything. It's a very rare occurrence for something to hit something else. So those asteroids, there's Star Wars, the Millennium Falcon is going through this asteroid belt. It has to dodge all of these asteroids. Do you think that's what an asteroid belt looks like? Well, not actually. So things in the solar system are very, very, very far apart from each other, even asteroids in the asteroid belt, and especially comets out in the Oort cloud. Okay, so I think I'm going to take one more question because we're going to get kicked out of this room pretty soon. Okay, you seem really enthusiastic over there.
Yeah, you said the density of this body is lower than the density of water.
Correct.
So upon impact with the Earth's atmosphere, it would still go through, or it would like disintegrate it.
Okay, so if a comet hit the Earth, if the comet is less dense than water, will the comet disintegrate, or will it hit the surface of the Earth? So it depends a bit on how big the comet is, but something like the comet that Rosetta is orbiting around, it will probably not burn up, and it would hit the Earth. Some of it would probably burn off, but there'd still be a core of fluffy, icy stuff in the center of the comet, which would probably hit the Earth and cause a big crater impact.
I mean, a body with this composition, would it be a danger?
So you would probably, yes, if this comet hit the Earth, it would be a very, very bad thing. So it might, yes, so maybe it would end all of human civilization is something that big, even a comet that big hit the Earth. So luckily, this one will not. Okay, thank everyone. Go see the telescopes and the comet making outside on the ground